First thing I want to do for problem 1 is create a Venn diagram. So I went ahead and did that over here on the right hand side, and it says this probability of a student passes physics is 0.91. So the probability of a student passing physics, we'll just do P of the probability of P happening is 0.91, which makes sense. That should be 0.80 plus 0.11. That's where I got this 0.11 from, adding those two numbers together. The probability of a student passing chemistry was 0.85, and again, the probability of passing both was the 0.80, and then I figured, oh, there's got to be a 0.05 that's got to go in just the chemistry section. All right, and then I got this 0.04 because that's what would be left over. It's all got to add up to 1. The probability is 1 that you're somewhere in the sample size. You either pass one, the other, both, or neither. Okay, so that should all add up to 1 now. Now, determine if the events are independent of each other. This comes back to section 7.3 in the textbook. All right, and when we're determining if two events are independent, what we need to do is we need to say, okay, the probability of the events times each other should equal the and, all right, if independent. So if these events are independent. So we just say 0.91 times 0.85, that should equal 0.8, okay? So 0.91 times 0.85. And what I end up getting is not 0.8, I end up getting something else, like 0.77 or something. 0.7735. So now I know these events are not independent.
Wait, so how do we know what they're supposed to equal, like the probability of P and C?
Yes.
How do we know what P and C is?
It's given to us right there.
Oh, never mind.
0.8. So, yeah, they told us that the probability that you pass both classes is 0.8. So if 0.91 times 0.85 equals 0.8, then they are independent. That means that the fact that you passed physics has no bearing on whether you're going to pass chemistry or not. But since they're not independent, that means there's some type of relationship, saying that if you don't pass one, there's some likelihood that you're not going to pass the other. All right, something like that. A randomly chosen student passed physics. Okay, so given that they passed physics, find the probability that they did not pass chemistry. So we're in this circle of our Venn diagram. And we know they passed physics, but they did not pass chemistry. There's the people that passed physics, but not chemistry, 0.11. So that's why it's nice to set up that Venn diagram. 0.11. All right, that would be it. Okay. And we can, if we want to put our notation in properly, we can say P and not C given that they passed P. So that's what it would look like. So they passed physics and not chemistry given that they passed physics. Okay. Or actually, I think you could just say P and not C. That would also work. Yeah, that would give you the same exact answer if you just said they passed physics and not chemistry. All right, that's what problem 1 looks like. Let's take a look at this problem here. So for starters, part A just says sketch a graph and shade the region. So normal distribution. It's going to be that bell-shaped thing. And we'll say it has a mean of 320, standard deviation of 10. So we'll go 330, 340, 350. We always like to go 3 standard deviations above and 3 standard deviations below the mean. 320, 310. Oh, sorry, 310 should be the next one down. So 310, 300, and 290 for those heights. And now it says just sketch on here and shade the region that H is greater than 335. All right, so H is greater than 335, and that's going to be this area. And because it was strictly greater than, I did the dash line. If it was greater than or equal to, I would do a solid line. But that's the idea for part A. Part B, the first time I saw it, I was a little confused by it, but hopefully it's not too bad when I explain it to you a little bit here. It's saying, hey, there's another probability on here, assuming that that this capital H is less than a lowercase h. We just need to figure out what the lowercase h is. And it's going to be equal to this exact same probability. So basically, it's saying that on the other side of the mean, so on this side, there's that 335. It's kind of hard to read there, so I'm going to delete that, or erase that. On the other side, there's going to be another point that's equidistant from the mean, all right, that h can be, lowercase h can be, all right? So I want you guys to see if you can figure out where it's going to go on the other side of the mean. What's the same distance from the other side of the mean that's going to give you the same probability? That's kind of what part B is asking.
So when it's formatted like that, it's asking us where that equidistant point from the mean is to that first probability?
Yes. So yeah, because it's asking us to find the value of h. So basically we're 15 above the mean here to 335, so we're going to go the other direction, 15 below the mean. And that's how we'd end up, it's giving me like 305 here or something like that. So that lowercase h is saying equals 305. If I were to write out the entire equation, it's saying, hey, let's find the probability that this is equal to that. And that's how we find that the lowercase h is 305, because you're finding on both tails of the graph there's going to be an equal probability. My graph's not drawn very accurately, but technically this probability is the exact same as that probability there. Okay? That's what that's saying right there. Okay? Now, part C, I'll let you guys work on that. Saying find the probability of the values between 305, the probability that you land between 305 and 335. So this one you're going to need your calculator for, but basically I'm asking you to find this area right here. So find that probability that you're going to land between 305 and 335. You guys should be able to do that on your calculators. So give that a shot now, and then see if you can do part D as well. It's an expected value problem. All right, so parts C and D I'm going to give you a few minutes on. Normal CDF, lower bound 335, upper bound 1e to the 99. So that just gives us infinity.
Wait, can we not do the lower bound 305 and the upper bound 335?
No, we could do that. Yeah, that's actually the easiest way. Might as well make it one equation. Yeah, duh. So 305 to 335. Brilliant. Easier than I was going to make it. Then you say your mean is 320, and your standard deviation is 10. Put that in your calculator, and you should get something like 0.86, I think. And that's your probability that this falls between these two values. All right, that's the idea for part C there. And then part D, the last one, in a delivery of 3,215 sunflowers, find the expected number of sunflowers that are not classified as tall. So that's going to say, when we get to that 335, we're going to find the probability that it falls below the 305. 335, I mean, because that's not classified as tall. All right. There's our mean. So 3,215 sunflowers were delivered. So what's the probability that they weren't classified as tall? So once we find the probability that they were less than 335, we multiply that probability by 3,215, and we'll get our expected value. So the expected value that they're not tall is going to be the probability that they're not tall times 3,215. All right. And again, you probably need to do normal CDF for that. My graph doesn't look very good, my normal distribution curve. It's going to be a little more smooth than what I drew. All right. But that's the idea for this particular problem.
So that's the expected probability of them not being tall?
Expected value of how many will not be tall, yes. So we do the probability that they're not tall first with normal CDF. And I don't remember what we get for that exactly, but it'll be most of them. And then we multiply that by 3,215, and we should get our expected value that they're not tall. And I think it comes out to about 3,000. Just round to the nearest whole number. So about 3,000 of them will not be tall. Okay.
How do we find the probability of not being tall? So we do
Normal
CDF.
Normal CDF again. Lower bound this time will be negative infinity. Upper bound will be 335. Yep. So that's just a normal CDF problem. Yeah. Okay. Moving on to problem 3 here. This is going to be section 7.5 in your textbook. So represent the probability distribution of S in a table. That's what part A is going to ask you to do. Part B represents the probability distribution of S as a function. So again, check out chapter 7.5 in your textbook for these particular problems. And then part C gives you an expected value problem. All right, so try problem 3, and I will be happy to answer those questions for you. Oh, and if you finish that ahead of time, problem 4, that's like a tree diagram, that's going to go into section 7.4 of your textbook. All right, so I'll give you the next couple of problems there for problems 3 and 4. So our probabilities, 1/16, we had 2/16 for 3, 3/16 for 4, 4/16, 3/16, 2/16, and 1/16. And then to write the equation, we would say something like, oh, well, like I have this value for the lowercase s. So like I notice that I'm going 1/16, 2/16, 3/16. I notice that the number s, the probability is going to be one lower than that. So you'd say something like s minus 1 over 16. And that s minus 1 is going to work for 1/16, it's going to work for 2/16, it's going to work for 3/16, it's going to work for 4/16. When I put in 2, 3, 4, or 5 for s, it's going to give me that appropriate probability. But when I put in 6 for s, 6 minus 1 is 5/16, and that problem doesn't work anymore. So that's why I need a different one for this equation down here. But I can say, okay, s minus 1 is over 16. That's going to work for 2 is less than or equal to s is less than or equal to 5. And then once I get past 5, 5 is less than s less than or equal to 8. I can go ahead and create a different one. This time though, I'm looking at 6, and I want to go 6 minus 3 is 3, 7 minus 5 is 2, 8 minus 6 is 1, so that's not going to work. So I can't do like a minus s. Or I can't do an s minus something here. It's going to be, yeah. So I think something like 9, I think, is what works for this one. 9 minus 6, 9 minus s. Yeah, 9 minus s is 3. 9 minus 6 is 3, 9 minus 7 is 2, 9 minus 8 is 1. That's kind of how you set these ones up.
How the heck are we supposed to be able to find that on the test?
Yeah, I'm not a huge fan of those problems personally. I'm just showing you this one. You probably won't see one exactly like this on the test where I'm asking you to find the probability distribution like that. I think asking you to set up the table in part A is a fair question. I think part B, that's kind of a tricky one. But that's the idea for these ones, yeah.
I'm also sort of confused on what the the probability of the big S equals the little s, like that's kind of confusing. What does that mean?
Sure. Little s is just a placeholder for the outcome. So big S is discrete, saying this is the number that's going to be. The little s is simply the placeholder, saying, hey, when little s equals 2, that's saying the probability that the big S happens. So big S is the actual outcome. Little s is the placeholder for the possible outcomes. Does that make sense? So it's saying what happens when the actual outcome equals the possible outcome. So when you get the outcome. I don't know. That's the best way I can describe it. It's kind of a little bit confusing there.
Yeah.
But
So there's more examples of that, right?
yeah. So basically the idea is little s represents all of the possible outcomes. I roll 2 die here, and my outcomes are 2, 3, 4, 5, 6, 7, and 8. All right. Big S is saying, what happens if big S is 5? So you actually get 5. So that's your actual outcome. That's all the S equals S means. Okay. It's just saying when you get an outcome. That's what it's saying. Let's look at part C. This is an expected value problem. And they give us a couple hints here. One of them is they say, find the value of X dollars to ensure the game is fair. So what happens is you win $1 more than you paid if S is a multiple of 4. You win $2 if S is a multiple of 6. All right. So the multiples of 4 are 4 and 8, right? Are 4 and 8. So the probabilities of a multiple of 4 are 3/16 plus 1/16, which is 4/16. Okay, that's
Okay, wait, can you restart? I'm kind of confused.
On part C?
Yeah.
Sure. So this is saying there's an expected value problem. Actually, let's start. So let's go a different route on this entirely, actually, before I get to that. So we had multiple of 4. So you have a possibility of a 4 or an 8. The multiples of 6, the only possibility is that you get 6. That's it. That's your one possibility for that problem. Now, if you get a 6, so you hit that probability, you're going to win $2 more than you paid in. If you hit a 4, you're going to get $1 more than you paid in. And otherwise, every other outcome, you're going to lose the money you put in. So find the value that makes the game fair, which means the kids that wrote the game, Anrai and Clara, they're not making money off of it. So basically, the expected value is 0. So we're going to say we are going to make $0 from this. So that's the probability that makes this fair. Find the value of money that you spend that makes this fair. So what that means is to get a 6, for example, the only probability that you have is 3/16. So you're going to do 3/16 times x plus 2 plus, and then you would say the probability that you get a 4 or an 8.
Wait, so how did you get the 0 equals 3/16?
Well, 0 because it says the game's going to be fair, so I'm not going to make any money off of it. So 0 is representing my total profit is going to be $0. And then what I'm going to do is I'm going to work out these 3 possible outcomes. You have the outcome that you roll a multiple of 6, and that's the x plus 2. You have an outcome that you roll a 4 or an 8. So getting a 4 or an 8 is 3/16 plus 1/16. And if you roll a 4 and 8, you win $1 more than you put in. That's 3/16 and 4/16. That's 7/16 right there. So otherwise, you're going to lose your money. So you're going to say minus 9/16 times x. And theoretically, this should come out to $0. Because I'm either going to make $2 more than I put in, I'm going to make $1 more than I put in, or I'm going to lose all of my money. So we're trying to figure out what's the initial investment amount that makes this game a break-even game.
Where did the 9/16, where did that come from?
The probabilities have to add up to 1. So there's 3/16 and 4/16. That's 7/16. And then plus 9 is 16/16. Because those are the 3 possible outcomes here. Your probabilities all have to add up to 1.
Oh, so that's just like that's making it so the total would be 16.
Exactly. Exactly. Yeah.
So that's the leftovers, basically.
Yes.
So subtract the leftovers.
Yeah. And now we have an algebraic equation we should be able to solve, hopefully. Negative 2/16 plus 10/16. And then for my expected value here, I should end up getting, like, the 16s go away and I get 10 divided by 2. So I should get x equals 5. So to make this game fair, it means I should be charging $5. So that way it's a break-even game. So I'm not expected to make any money. I'm not expected to lose any money if I'm putting the game on. Okay, that's what this expected value problem's asking us to do. So I mean, it looks a little intimidating at first when you see that type of problem. But you have to be able to say, okay, multiple of 4, what's that mean to me? 4 and 8. What are those probabilities? Let's multiply that by the expected outcome. Multiple of 6, what's the probability? Multiply that by the expected outcome.
So what did you do at the negative 10 over 16 equals negative 2 over 16x? What did you do there?
Oh, so sorry, I skipped a step. You multiply by the reciprocal of both sides, so 16 over 2. Because 16 over 2 times 2 over 16, that's going to become a 1. And then on this side, you get 16 divided by 16, that goes away, and you have negative 10 divided by negative 2. And that gets you a positive 5. So yeah, it's just about multiplying by the reciprocal there. So we have dispenser P. And the probability of dispenser P failing was 0.007. The probability of it not failing, 0.993. And then we go to the next one, dispenser Q. And it's going to have 2 possible outcomes.
Oh, I did them all like separately, like.
Okay. I think it's going to work better because if you do it this way, you can see all of the routes. I think, I don't know. It's really up to you though, whatever works best for you. I'm going to run out of room here. And then the last one, there's going to be like 4 branches off of that one. So yeah, the last probability. But then you can see the probability that all 3 failed goes up the very top. The probability that none of them failed goes down the bottom. All right. So that's one way to do it. The other way you can do it, so if you don't want to do the tree diagram, think about the probability that exactly one of the dispensers malfunctions on a given day. That means you could say the first one fails and the second one does not, and the third one does not. Okay, that's one possible outcome. Exactly one fails. But there's the possibility that the first one works, and the second one fails, and the third one works. See how that works? That's a way we can do it without creating the tree diagram, which might be a little easier for this problem because otherwise you're creating 8 different branches on a tree diagram. And then the third possibility is that the first one doesn't fail, the second one doesn't fail, but the third one does fail. Oh, I'm just running out of space today. I'm so bad at this. Okay, let me write smaller, zoom in. I'm going to delete it and I'm going to just rewrite it a little smaller, guys. But again, when we're doing exactly one of them fails, 0.007 times 0.997, that's the probability that this one does not fail, times 0.999, that's the probability that this one does not fail. And now we switched up 993, 003, and 0.999, and then the last one, 0.993, 0.997, 0.001. Add all 3 of those together, and that's your probability that exactly one of them fails. Those are the 3 scenarios where one of them fails and the other 2 don't. Okay? And then part B says, find the probability that at least one of the dispensers will malfunction on a given day. So on this one, it's probably going to be easier to find 1 minus the probability that none of them fail. So if I do 1 minus the probability that none of them fail, then that takes away the probability that they're all working. And then what's left is you have the probability that at least one of them fails. Okay?
Wait, so what was that? That's 1 minus probability none fail?
Exactly. So that's 1 minus the probability that none of them fail, because then we're going to get the scenario that at least one of them fails, maybe 2 of them fail, maybe all 3 of them fail. This is taking away the one branch that none of them fail on that 8-branch tree diagram. It takes away really fast. Okay. And I think if you can, if you need to visualize it with the tree diagram, then great, do that. And then just be very careful and diligent and highlight the routes where exactly one of them happens. And if we did that, highlighting the routes, we would come up with these 3 possibilities. All right. And then the one that none of them fail, that's what's happening down here. Okay. And that's what we come up with for our numbers for this particular problem. Okay, so I think part A, when I worked it out, I got something like 0.010938, something like that, for the probability that exactly one of the dispensers fails. So it's like a 1% chance that one of them fails. Super small percentage. And then the probability that at least one of them fails shouldn't be that much higher than this. I think it came out to 0.010969. So again, super small probability that that a coffee maker is going to fail, which makes sense when you're multiplying 0.993 times 997 times 999. You're not getting huge numbers, or you're going to get a huge percentage that works. All right. That's problem 4. Shoot, we only have 10 minutes left, so problem 7 is a That's an IB question. So this is like an IB test question. This is from an actual IB exam, just like what we did last time. Okay, so it covers a little bit of everything from this section. Okay. Ooh.
Should
Alright.
we do the test tomorrow so we get a little bit more time to do this?
Should we what?
Should we do the test tomorrow or Wednesday so we get a little bit more time to do this?
I was gonna have you guys do the test on. I was gonna have you guys do the chapter 6 second opportunity on Wednesday. So we are doing this test tomorrow. But if you guys have questions before class, I'm more than happy to answer those questions. So if you guys come to the start of class tomorrow with questions, I can definitely answer those questions. Problem 5 says solar power traffic speed monitor is in the design phase. So there are 6 cells, and the power provided will provide at least one of the cells is working. The cells function independently of each other, and the probability that a cell fails within 1 year is 0.75. So it's a very high probability that one of them fails. But there are 6 cells that work independently of each other. Find the probability that a prototype with 6 solar cells will cease to function within 1 year. So what that means is one cell needs to still function. So if you did 0.75 times 0.75 times 0.75, or actually we'll make this easier because they're independent, we can do 0.75 to the 6th. 0.75 to the 6th is going to give us what? 0.17, so it's like you get a 0.17 probability that this fails.
Isn't the probability that they all fail?
That's the probability that every single cell fails, and the whole system fails only if all of them fail. So it comes out to something like that. So if we want to find the probability that not all of them fail, we're going to do 1 minus 0.75 squared. Or to the 6th, I mean. And that we're going to get 0.82202, something like that. So there's like an 82% chance that this thing's still going to be working 1 year later, because at least one of the cells should still be working 82% of the time. All right, the manufacturer wishes to market with a guarantee that the product will still be operating at the end of the year is at least 0.98. Find the smallest number of cells that the SPTSM should have in order for this to be the case. So in this case,
why is it true that it's 0.82?
why?
So that's the.
So what's happening is we're saying this thing functions as long as one cell is functioning. So if all 6 cells fail, then this is the percentage of times it's going to fail. About 18% of the time it's going to fail. Okay. Or so we do one minus the percentage that it's failing, and that's the percentage that it's not failing, is 82% of the time. So what we want to do then to prove 98% of the time, it's almost like a guess and check. We're going to have to say, let's do 7 cells, or let's do 8 cells. Or actually, you can do better than a guess and check, I guess. We can do 1.75 to the x equals 0.98. And then we can subtract 1 from both sides, and we would have to undo this, which we learned this last year. Would have been logarithms, right? You take a log of both sides to solve for the exponent. So you guys might remember that. That would be how we do this algebraically. But you could do a guess and check method and do minus 1.75 to the 8th, minus 0.75 to the 9th, minus 0.75 to the 10th. If I do this algebraically, I'm going to get a negative 0.02, and then 0.75 to the 0.02. And then I take a log of both sides. And I get like log of 0.75 times x equals log of 0.02. X equals log of 0.02 divided by log of 0.75.
logs be on the test?
Will logs be on the test? No.
Like,
This
do we
one,
have to
this
start
one,
with
you
logs?
this one you can do with a guess and check. You don't need to know logarithms to do this problem, but this is an example of like an IB test question where it's going to intertwine other things that we've learned in the course, and because it's a 2-year course, this is why we talked about logarithms last year. Does that make sense? So this is just an example of something that you could see on the IB exam. For this one, I like this problem because you can guess and check. You can just do this and keep going up and going up and going up until you find a value that works for you. In this case, it comes out to 13.5. So you need x to be approximately 14. So you need 14 cells for this thing not to fail on you. That's the idea for part B there. But will logs be on the test? I mean, it's a possibility I put a problem like this on the test, but you don't need to know logarithms in order to do them because you could just do the 1 minus 0.75. But for those of you that are thinking about taking the IB exam, this is a real problem that you could see on the IB exam where it's like, it's going to be a probability problem, but then all of a sudden there are logarithms involved because that's what they like to do. They like to intertwine several topics into one. All right, and that's what makes the IB test really tough, is these types of problems right here. Okay? So again, you could just do a guess and check method, which is what I was showing over here. Just keep plugging in higher numbers for the exponent. Or you could solve algebraically using logarithms. Okay, either method works. Okay. Now, problem 6. Ricky has 2 bags containing beads. A bag A contains 6 red beads, 2 green beads. Bag B contains 5 and 3. Ricky chooses a bead at random from bag A and places it in bag B. He then chooses a bead at random from bag B. Construct a tree diagram to represent the possible outcomes of the above situation. On each branch, write down the probability. So, in say bag A, he's got, oops.
Are we going to make 2 separate ones for bag A and bag B?
No, we can do one. What we do is we do bag A, and he's got 6 red out of 8 possibilities, and then he's got the possibility that he doesn't get a red, which is a green one. Okay, so this is the probability of a red, the probability of a green. Now what happens is he's going to put that marble into the other bag. So the other one had 5 red and 3 green. So it's technically going to have 6 red now out of 9 marbles on this line, and that means on this side it's going to be the probability of a green was 3 out of 9. And then the other possibility was if you did the probability of a red, the probability of a green, it would be 4 out of 9 here and 5 out of 9 over here. Those would be your possibilities. And then it says,
Wait, what? Where'd you get the 5 and the 4 from?
the 5 and the 4. So
Oh, wait.
what happens is on the first bag, he's got a red bead or a green bead. He pulls out, let's say he pulls out a red one. And now he's putting that red one into the second bag. He's going to shake that second bag up, and then he's going to pull out a marble. So he's adding, or pull out another bead. So he's adding a bead to the second bag. So even though the second bead starts with 8 beads, it's really starting with 9. And that's where we get the probability of 9 from. So what happens is if he pulls out a red one, the other one had 5 red ones. But now if we go on this course, it's going to go to 6 red ones. And then there'd be 3 that are not red, the 3 green ones. If we go to the other course, he's adding a green one, so it's going to go from 3 to 4. And that means the other one's still going to be a 5. Kind of a weird problem there. And so let's find the probability that he chooses 2 beads of the same color. So the odds of him choosing 2 beads of the same color, 6/8 and 6/9, or 2/8 and 4/9. So we can add those together. So 6/8 times 6/9 plus 2/8 times 4/9. And those are the possibilities that he gets the same color. So 36/72 plus 0.8 over 72 equals 44 over 72. And then we can simplify that. And I think it simplifies to 11/18. All right. Or you can just turn it into a decimal and you get 0.611. All right. That's the probability that he pulls something out that second time. Okay. That's what problem 6 looks like. But again, construct the tree diagram. Trying to make sense of what it's asking is very important. Okay. All right, last problem. This is an IB test question from a few years ago. The following table shows the probability distribution of a discrete random variable is this. Okay, it gives you the table already. And now it's an expected value problem. Given that the expected value equals 2.45, find alpha and beta. Whoops. So you'd say 2.45 equals, and your probability of alpha is 1 times 0.01. Or I'm sorry, your first probability is 1 times 0.01. Second one's 2 times alpha. Third one is 3 times 0.01. Fourth one's 4 times 0.15. And the last one's 5 times beta. Okay. And one of the keys is that we know that, let's see, did I leave something out of this one? I might have left some wording out of this one because I think it was given that alpha was less than beta. I could be wrong. Nope, that's all that was given to us. Okay, so yeah, what we do is we do the 2.45 and then times all these probabilities. Okay, and then we're going to solve for alpha and beta. And remember, the probabilities have to add up to 1, so that's part of it as well. So we can actually write a separate, that's what we can do. We can write a second equation that says all the probabilities have to add up to 1. 1 equals 0.01 plus alpha plus 0.01 plus 0.15 plus beta. Not 0.01, 0.1, but yeah. All right. And that's what you would do for this problem. You set up a, what's it called? A system of equations. That's what it is. 2 equations. You can solve for alpha in one of them and solve for beta in the other. And then plug in and solve for the other one. So that's kind of what's happening with part A here. And like I said, this is an actual IB question. That's what's happening for this particular problem here. Do you guys need to see how to solve this system of equations, or do you remember how to do a system of equations when you get it set up?
Can you solve it, please?
Sure, no problem. So let me zoom over here to the right. I'm going to give myself a little more room. What I can do is I can get like alpha by itself on one side and say 1 minus 0.1 minus 0.1 minus 0.15 minus beta. And that's what alpha equals. So now I can take this entire thing and I'm going to plug this in for alpha, and I can simplify it, minus 0.1 minus 0.1 minus 0.15, and plug it in over here. That's the trick for this particular problem. 2.45 equals, we'll do 0.1 because I was 0.1 there, plus 2 times, this is minus 0.35, so 0.65 minus beta. After I simplified this, this comes out to 0.65 minus beta. That's where I got that from. And then plus 3 times 0.1 is 0.3. Plus 4 times 0.15 is 0.6. Plus 0.5 beta. Okay.
Are we going to see anything like this on our test?
It's possible, yeah. This is an actual IB question, so, and
I
it's
mean, not. I mean, like on our test tomorrow.
yeah. So I mean, I'm gonna put I'm gonna put probably one IB question on the test tomorrow. It'll be at the very end, but yeah, it's possible to see a problem like this. Yes. So I mean, just this is just the this is just something that kind of encapsulates everything that we've done in the chapter. All
Can you
right.
move to the right a little bit?
Sure. All right, and now we get 2 times 0.65 times beta. And we can add the 0.1 and the 0.3 and the 0.6. That's going to be a 1 plus 2 times 0.65. That's 0.325, right? Or 65 times 2 is 1.3. 1.3 minus 2 beta plus 0.5 beta. All right. 2.45 equals 2.3 minus 1.5 beta. And I get 1 point, nope, not 1 point. I'm going to get 0.15 equals negative 0.15 beta. Right?
How come you didn't add the 0.3 and 0.6?
I think I did. I did 0.9
Oh.
plus 0.1 is 1. That's where I got this one from. So the 0.3 and the 0.3 and the 0.96 is 0.9, and then that's plus 0.1 is 1. Unless I did some math incorrect somewhere along the way, which is possible. I'm going through it kind of fast, sorry.
Why is it 0.5 beta?
Why is this 0.5 beta?
Yeah.
Oh, sorry, it should just be 5 beta. You're right. Sorry. Yeah, it should be 5 beta. I don't know where the 0.5 came from. It's 5 beta over here, so. Yeah, so it should be a 5 beta. Thank you.
Can you move over to the left a little bit?
Yep, I'll zoom out. Come on. I'm gonna try and zoom out. There we go. So it should be that should make it, instead of a negative 1.5 beta, that should make it a plus 3 beta. And that means beta equals 0.05. And now I just go back in and plug in 0.05 for beta up here, and I can figure out what theta is, what alpha is going to equal, which should be 0.6. All right, and that's what this problem looks like here. Okay. So again, on the test tomorrow, most of the problems will be very specific, like problems 1 through 6, like to this section of the textbook. There's probably going to be like one problem that will be specifically an IB question that kind of incorporates everything that we've talked about so far. All right, but part A on this one is that's an expected value problem where we have to set up a system of equations to solve it. That's a pretty tricky problem. Okay.
Is that going to knock us down significantly if we don't get that right?
I'm sorry, if you don't get that right, what?
Are we still going to be able to like get a 4?
Yeah, that's fine. And the other thing about the IB test is even if you don't get part A, you can still get part B, where it says find the probability that x is greater than or equal to 2, given that it's less than or equal to 4. You just do it in terms of alphas and betas. You want to be able to solve everything. All right. But this one says, given that it's less than or equal to 4, which means we're going to take this part out of the equation completely, which is the 0.05. So this probability would be 0.95 on the bottom. And then the top, that is greater than or equal to 2, 0.6 plus 0.1 plus 0.15. We're going to just take out the 1 at the beginning for the 1. So we get 0.85 divided by 0.95. And that's going to be our probability that it's greater than 2 and less than or equal to 4. And we should get something like 0.8947. All right, so you have probably about a 90% probability that you're going to get between 2 and 4. Get greater than 2, given that it's less than 4. All right. Part C, 2 random observations of x are taken. Find the probability the sum obtained is greater than 8. So we're going to take an observation, and then independently we're going to take a second observation. What's the probability that it's greater than 8 when we add them together? The sum of those two. All right. So that's more of a, like an outcome where we look at, whoops. I'll zoom in a little bit on this last one. Whoa. So this last one is going to be more like if we created the table, like the dice roll, and we say there's a possibility of 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And so it looks like there are going to be 25 outcomes of sums, right? The sums that are greater than 8, they're going to have a 10, a 9, a 9, an 8, an 8, and an 8. And then this will be 7s, 6s, 5s, 4s, 3s, and a 2. But all the ones that are greater than 8, there's 1, 2, 3, 4, 5, 6 out of 25 total possibilities that you're going to get the sum of is greater than 8. So this one has to rely on us being able to create a probability distribution table and kind of figure it out from there. All right, a sum of two numbers. 6/25 is your probability there.